All right, so now that you've been introduced to the gas laws, now it's time to solve some problems using them. The first problem is, how do you know when to use which equation? So here we have the combined gas law on the left and the ideal gas law on the right. By the way, instead of saying before and after here, we could instead use ones and twos. So I could say that P1 V1 over T1 is equal to P2 V2 over T2. This is a more common way to write it rather than before and after scenarios. All right, but one way to realize that which equation you should use is if you do have two values of the same variable, you're obviously not using the ideal gas law. If as you read the problem you notice that there's like a before situation and an after situation, then that would tell you to use the combined gas law. If there's no mention of moles, because remember the combined gas law does not address concentration at all, then you would be using this one. Or if there's only two variables addressed instead of all four, then you can be using the combined gas law. And the reason that works is because if one of these values, pressure, volume, or temperature, is held constant, then we can ignore it in the equation. So we just basically cover it up and just pretend it's not there. If you need to use the ideal gas law, you would notice that your problem only has one value for each variable, or it will mention moles. So that's a good way to tell which gas law you should be using to do your problems with. Regardless of which equation you choose to use, there are some rules we need to follow. First of all, if they mention STP in the problem, then you know two values. You know that at standard temperature and pressure, the standard temperature is 273 Kelvin, and you know that the standard pressure is 1 atmosphere. So just by them saying STP in the problem, you know two values that you can list in your variables. Your temperatures must all be in Kelvin. Whenever you're using gas equations, you have to be in Kelvin. So yep, you got to be able to convert from Celsius, but that's easy because Kelvin is just Celsius plus 273. So that's really easy to convert from one to the other. And then the other thing you need to know is that your temperature and pressure units must always correlate. They always have to go together. And if you happen to be using that R value, remember that R value has units of liters, atmospheres, moles, and Kelvin. And so if you're using the ideal gas law, your volumes have to be in liters, your pressures have to be in atmospheres. And so you may have to do some more converting. I just have four really basic quick equations that I'm going to go through very quickly for you because you can always pause and go back. So our first problem here says a sample of air has a volume of 550 milliliters at 106 degrees Celsius. At what temperature will its volume be 700 milliliters at a constant pressure? So the first thing I notice is that it seems like I have a set of before conditions and a set of after conditions. So because I see a before and after scenario, I'm going to guess that I'm going to be using my combined gas law. So that's P1 V1 over T1 equals P2 V2 over T2. So this is the equation I'm most likely going to be able to use. Other than that, I'm going to go back to the same problem-solving process that I've been teaching you. I'm going to look for the question word first. Here it is. What temperature? So temperature is what they want me to find, but is it the before temperature or the after? You'll notice here it's the after, so T2 is what they want me to find in this problem. And then for all the other numbers, I'm simply going to list them and identify their variables. So the first one is 550.0 milliliters. Milliliters is a volume, and it's part of my before condition, so that's volume 1. I have 106 degrees Celsius, but I can't leave it in Celsius. I have to convert it to Kelvin. 106 Kelvin is actually 379. I'm sorry, 106 Celsius is 379 Kelvin. That is a temperature, and that temperature is also part of my before condition, so that's T1. They want to know what the temperature will be, so there's my T2, if the volume is 700 milliliters, so I have 700.0 milliliters. Notice that I have milliliters and milliliters. That's good. They correlate, so I don't have to worry about converting those. And this is going to be another volume, but this is the volume in my after scenario, so I'm going to call this V2. And then they tell me that the pressure is constant, which means I can ignore it in the combined gas law equation. So I can only ignore things when I'm using the combined gas law. So to ignore it, I'm just going to pretend that it's not part of the equation because it's going to be the same on both sides, and so it won't affect my math. Well, the first thing I do is I identify, well, T2 is what they want me to find, and uh-oh, T2 is in the denominator, and that's bad. I've told you, you never want to solve for a variable that's in the denominator. You want to get it out of the denominator first. So the first thing I'm going to do is I'm going to get this out of the denominator. I'm going to choose to cross multiply to get it out of the denominator. So I have that V1 times T2 is going to be equal to T1 times V2. And then I want to get T2 all by itself. So to do that, I'm going to divide both sides by V1. So I get that T2 is equal to the first temperature times the second volume divided by the first volume. Now, I'm not going to take the time to substitute all these numbers into here, but I will take the time to show you what's going to happen to their units. So this temperature, T1, is in Kelvin, so I have a Kelvin on top. V2 is in a unit of milliliters, and V1 is also in a unit of milliliters. So the milliliters and the milliliters will cancel, and so my final unit should be in Kelvin. All right, which is good because it's a temperature. Now, if you plug in these numbers and run it through your calculator, the number that you get, let me switch back to my yellow pen here, the number that you get is 482.36 Kelvin. But then I go back to my problem to check for significant digits. In 550.0, there are 4 significant digits. In 106, there are 3. And in 700.0, there are 4. So I only need to have 3 significant digits. The 3 tells me to leave the 2 alone, and so I end up with 482 Kelvin as my final temperature. Here's another example. It says a sample of gas at 104 and 0.870 with a volume of this. Then it tells me what volume will it have if I change the conditions. So once again, it looks like I have a set of before conditions. So these are my before. And then this is my after. Because I noticed that we have before and after conditions, I'm going to predict that we're going to use the combined gas law. My question word is what volume, so V is what I'm trying to find. And I'll notice that this volume is part of my after conditions, and so V2 is what I'm trying to find. So V2 is what I want to get all by itself over here. Then my first number I run across is 104 degrees Celsius, which happens to be 377 Kelvin. And this is my initial, notice it's my before temperature. I then have 0.870 atmospheres. That is a pressure, and that's my before pressure. And then I have 3.00 liters. Liters is volume, and that happens to be my before volume. They want to know what volume will I have at 60 degrees Celsius. So 60 degrees Celsius is a temperature. It happens to be my second one, but I need to convert it to Kelvin, which is 333 Kelvin. And then I have 1.7 atmospheres, and that would be my second pressure. To solve this for V2, I'm going to multiply both sides by T2 over P2 so that the P2 and the T2 will cancel, giving me V2 all by itself. But if I do it to that side, I've got to do it to this side. So I end up that V2 is equal to T2 times P1 times V1 over P2 times T1. Once again, I'm going to show you what happens with the units. So this temperature will be in Kelvin, this pressure will be in atmospheres, this volume will be in liters, This pressure will be in atmospheres. This temperature will be in Kelvin. So the atmospheres cancel, the kelvins cancel, so I should be left with liters. So when I get my final answer should be in liters. Once again, I'm not going to plug these values in over here. I think you can do that, but if you plug them into this equation and you run it through your calculator, you will find that you get 1.356, and we already discussed that I should get liters. I go back up and I notice that the fewest number of significant digits is 2. Oh, by the way, it really should only be 1. 60 is only 1. So if it's only one significant digit, then this would just be 1 liter. So my answer here is incorrect. I counted 2 significant digits for 60. So here's a different kind of gas problem. Here you'll notice it says, what is the volume in liters of 2 moles of fluorine gas at 100 Kelvin and 1.5 atmospheres? Notice that there's no before and after scenarios, so since there's not, I'm going to predict that I'm going to be using the ideal gas law, PV equals nRT. I'm still going to start with my question word. They want to know, what is the volume? So volume is what I don't know. So volume is what I'm trying to solve for. Then I have 2.00 moles, and so that would be N. I have 100 decimal point Kelvin. That's to tell me that there are 3 significant figures there. That's a temperature, and it's already in Kelvin, so I don't have to convert it. And then I have 1.50 atmospheres. That's a pressure, and it's a good thing that it's in atmospheres, because if I'm going to use R has atmospheres in it. And then I realize, oh yeah, what am I going to do about that R? Well, I can list R here. It's something I had to memorize. It's not given to me in the problem, but it is 0.0821, and my units are liters, atmospheres, over moles, Kelvin. So if I rearrange this to solve for V, I'm going to divide both sides by P so that the P's cancel. And I get that V is equal to nRT over pressure. Once again, I'm not going to substitute values in for you. I think you can handle that and run it through your calculator, but I will show you the unit analysis. So this is going to be in moles. R is liters times atmospheres over moles times Kelvin. Temperature is in Kelvin, and pressure is in atmospheres. So this mole and this mole cancel because this one's on the top, this one's on the bottom. Kelvin and Kelvin cancels. The atmospheres cancel, so I'm just left with liters, which is good. And so if you run this through your calculator, you will find that you get 10.946 liters. I go back, I have 3 significant digits, 3 significant digits, 3 significant digits. So I need the 10 and the 1, the 0, and the 9. The 4 tells me to leave the 9 alone, so I get an answer of 10.9 liters. And finally, we have calculate the number of moles of gas contained in 1 liter at 273 Kelvin and 1.5 atmospheres. Once again, I do not have before and after scenarios, so I'm going to assume that I'm going to be using the ideal gas law. Here I don't have a question word, but I have an instruction word. It tells me to calculate something. They want me to calculate the number of moles. So moles is N, and so N is what I don't know. That's what I'm trying to find. So N is what I'm going to need to get all by itself. The first number given to me is 1.0 liters. That is a volume, and it's a good thing that it's in liters because I'm using the ideal gas law. I have 273 Kelvin. That is a temperature. Also good that it's in Kelvin. Don't have to convert it. And then I have 1.5 atmospheres. That's a pressure. Also in the correct unit for using R. And then I go, oh yeah, I need R. R is what I have to memorize. And it's 0.0821. And my units are liters times atmospheres over moles times Kelvin. So to solve this for N, I'm going to divide both sides by RT. So the RT's cancel. So I get that N is equal to PV over RT.